Hi, everybody. Let's get into our first lecture on 2.2 and 2.3. I'm just going to bring it up. Okay, hopefully you see that. Chapter 2 is all about this new concept called the limit. So we're going to spend a whole chapter just developing the concept of the limit. You can see 2.2/2.3 is our introduction. I'm going to combine those two sections from our textbook. I think it flows a little bit easier that way. 2.4, we talk about the precise definition of the limit. 2.5, we advance the idea of the limit to include continuity. It's going to be really important for where this is going at the end of the chapter. In 2.6, we talk about limits at infinity. 2.7 is kind of the goal of the chapter, is to develop and define the idea of the derivative. So we have a derivatives introduction, and in 2.8, we take that one step further with the definition of the derivative, and that will set us up for the next chapter and really the whole basis of the course. Limits are the basis for all calculus, both branches, differential calculus and integral calculus. Obviously, we start with differential calculus. Okay, so let's get into our limits introduction with this example. So limits, they're fairly intuitive. We can just dive right in. So kind of pardon some of the crudeness of this image that I created, some of like the choppy lines and kind of the funky. Okay, well, but I think it'll work for us. So imagine this function, and we're going to ask this question here. So we see the notation for a limit. We abbreviate it LIM, and underneath we write x, at least in this example, x arrow -2, and then to the side of the LIM in that same size font, if you will, is our function f of x. So we would read this, and I'm going to have this on the screen in another moment. We would read this as the limit of f of x as x approaches -2. So what we're going to do is we're going to say, okay, I see x equaling -2 is here on the graph. When we say the limit as x approaches -2, we're thinking, okay, if I was to, kind of find where the function is there, and I was to move away a little bit and then kind of trace it back. So as the function is approaching x equals -2, as I'm getting closer to x equals -2, where is the y value going? So here, and there's kind of two sides to it, right? There's the left and the right. So I'm coming in closer to x equals -2, and that y value is getting closer to 3. Same thing is true on the other side. If I move away from the point and then I start walking back toward it, here it's just a horizontal line. If I start coming back in towards -2 from this other direction, I'm still approaching the same y value there at 3. So the answer to this one, and it's probably not too much of a surprise, the limit of f of x as x approaches -2 is equal to 3, where that point is located on the graph. And there it is, written out in words, how you would read that notation. Notice I've underlined the word approaches. So we're not saying what is f of -2, like just where's the point, like, we're kind of used to. We're saying, no, it's not quite that. But as you kind of back off and then approach -2 from either direction, where is the function approaching what y value? Now here it turns out it's the same as the point itself, but that's not always the case. Let's take a look at part B here. The limit of f of x as x approaches 4. Okay, so I see 4 down over this way. And now a big difference from the question we were just looking at, this point is not filled in. We'd say that's a hole. The point is missing right there. But we can still use this idea of the approach, right? There is no point at x equals 4. but we can still kind of back off a little bit and then approach it, so we're kind of coming down. We can say, okay, well, what y value are we getting closer to? What y value are we approaching? And if we go from, this left side, and then we look at it again from the right side, they are coming to the same location. That's not always going to be the case, but here it is. And those y values are approaching 1. So this is interesting. Even though the point itself does not exist, is missing in the graph, we're still approaching that y value of 1. So the answer there is 1. And kind of the point being, it doesn't matter that the point is missing. What matters is, what are we approaching? Okay. Let's take one more example from this graph. How about the limit of f of x as x approaches 1? There's 1. Ooh, okay, something interesting happening on the left side. As we get closer to 1, the y value is headed towards 3. Well, it's actually staying at 3, but we could say it's approaching 3. But on the other side, on the right side, as we approach 1 from this direction, the y value is getting closer to 4. They're not the same location. Well, it turns out our answer here is does not exist, or usually we see that abbreviated DNE. If the left side and the right side disagree, they're not going to the same location, then we say the limit of f of x as x approaches that x value at 1 does not exist, or is DNE. And kind of a note there at the bottom, f of x must approach the same y value on both sides, the left side and the right side. It was the case for the other two, but not for that one at 1. Now you might think, well, that's there kind of was somewhere where we were headed this way and this way. Is there any way to kind of make sense of that? Do we always look at the two sides of the point? All of these cases, yes, but we can add a little bit more notation if we only want to look from one direction. Okay, let's look at part D. Let's approach the limit of f of x as x approaches 1. And now you see we have a little negative sign as a superscript after the 1. That little negative sign tells us to only approach x equals 1 from the left. And I think we use a negative sign. My best guess is because the negative numbers appear on the left side of the number line, the positive numbers on the right side. So when we say negative, we mean go to the left, or you might also think like numbers that are just a little bit smaller than 1. So what would the answer here be? Well, if we only approach 1 from the left side, we do have an answer. We are ignoring the other side completely. It doesn't matter what's happening there. We only approach from the left, and our answer is 3. That's from the left side only. But if we wanted to do the right side, well, similar, but we're going to put a little plus sign as the superscript after the 1. Little plus sign, well, the positive number is on the right side of the number line, I guess. And so this means only look at numbers that are a little bit bigger than 1 and then kind of work your way back. And there we have it. On the right side, we are approaching 4. These are known as one-sided limits, where the previous style parts A, B, and C were all two-sided limits. Also kind of notice one difference between parts D and E. Notice here at 1 that there's an empty circle. The point is not located there. It's located up here at the closed circle, the point itself. But that doesn't affect the answer to the limit, right? Because it turns out it doesn't matter what happens when you actually arrive at x equals 1. What matters is, what are you approaching? That key word. What are you approaching? Well, we're approaching 3. The actual point's up here at 4, but that doesn't matter. We're approaching 3 from this way, or from this side, we're approaching 4. Again, the point's there, but that doesn't matter. It's what are we approaching? Okay. moving on. Well, I guess one last thing I wanted to mention here, kind of, what might we call these kind of irregular things happening on the graph? A missing point like this, we would refer to as a hole. You might have even heard that language in pre-calculus. You do study features like this, and maybe they called that a hole in the graph. Things like this, maybe, maybe not, where there's that, literally a jump. The left side is going in one direction, and then there's a leap, and then the right side continues from somewhere else. Well, a jump is a pretty good word for that. So where we want to go, where this is going, and like more difficult examples, we almost want to think to ourselves like, if as we are being asked about a limit, is there a jump at that location? Is there a hole, right? If so, we have to be really careful about how we go about finding the limit. Let's say if we're not given a graph. Okay, which is what we're going to do now. How are we going to make these things more difficult? So I've got a few examples for us. 6 examples, as you can see. We'll see if we get through all of them in this video. We might have to stop in the middle. Okay, determine the limit. So these are going to be a little bit harder. We don't have the graphs. You're like, well, how are we going to do this? Okay, well, let's think it out. So what I'm going to do is transition here to my other camera. And hopefully you guys can see that. We're just going to work these out on paper. Example, determine the limit. And part A, let's see if I can get this to focus just a little bit better. Part A, this is how you would write it out by hand. Usually people use cursive. You can write LIM in print, but the kind of the conventional way to do it, maybe it's a little bit old school, is to use cursive. Can I get this to focus just a little bit better? Okay, maybe that might be as best as I can do. Okay, so let's think about this. The limit of 5x cubed as x approaches 6. So even though we don't have the graph, we could still think about this idea of, is there a hole or is there a jump? Does f of x equal to 5x cubed have a hole or jump where we're taking our limit, x equals 6? Okay, and we can think, well, 5x cubed. No, I mean, that's a cubic. It looks pretty much like x cubed, right? It's kind of, just to like give a quick sketch in your head, it looks something like this. Now the 5 makes it a lot steeper, right? So it's kind of like stretched out, but no, there's no hole or jump for 5x cubed. If there's not, the answer to this question is quite straightforward. We're simply going to plug in x equals 6. So we can just take 6, put it right in. I'm going to show you what I mean, 5x cubed. All we got to do is say, okay, well, that's 5 times 6 cubed. Grab my calculator. 5 times 6 to the 3rd. 1080 is our answer. What's happening is, like, if we were to graph it, where 6 is located, nothing unusual. The point is right there, right? So all we got to do is locate where that is. It's at 1080. Well, coming from the left side, right, it's headed toward that point. From the right side and back, back down, it's headed toward that point. No problem. That's kind of like the first example, the part A we had in the previous example. Both sides were going to the point was there, we're all good. How about this one, part B? gets a little bit more interesting. The limit x is approaching 0, and it was x squared minus x minus 6 all over x minus 3. Okay, well, I have no idea, honestly, what this graph looks like. So how are we going to do this? Hey, you know, we can still ask ourselves the same question about x equals 0. Is there a hole at 0? Or is there a jump at 0? And the answer is going to be no. How do we know this? Check it out. Try to plug it in, and let's see what happens. If we just plug the 0 in, we're going to have 0 squared minus 0 minus 6 over 0 minus 3. That's going to be negative 6 over negative 3. And we have an answer. Boom, we got it. Our answer here is simply 2. How do I know that? Here's the thing. The only thing unusual about this function here doesn't occur at x equals 0. It occurs at a different x value. You might think, what's going on there? Check out my denominator, x minus 3. If x was equal to 3, that would be a problem, right? It's undefined. But everywhere else, it is defined. And it turns out this is a rational function. And without going into all the details just yet, a rational function, if we're allowed to just plug in the number and we get a result that's defined, then we're good. So I'll just leave it at that for now. You say like x equals 0 is okay. Okay. Well, that leads to part C. We're going to take the same function, but now, of course, we couldn't not do this. We've got a big problem. The limit of x squared minus x minus 6 over x minus 3 as x approaches 3. Okay. What to do? So it turns out there is something unusual happening at x equals 3 graphically. It's not simply that it's undefined. The function would be undefined, but there will be an answer to the limit. Let's kind of explore this. Let's see what happens. If we were to try to plug in, what would happen? What would result? We know it's not going to lead us to an answer, but let's just kind of explore it. Plugging in x equals 3. Let's see, 3 squared minus 3 minus 6 over 3 minus 3. And it turns out, sure, we get the 0 in the denominator, but something else very interesting happens in the numerator. What do we have here? 9 minus 3 minus 6. That gives us 0 as well. Ooh, weird. Didn't see that coming. Okay. If, when we attempt to plug in, we get 0 over 0, that tells us there is a hole. And in this case, at x equals 3. There will be an answer to this limit. At a hole, it's simply that the point at 3 itself is missing, but the way it's approaching from the left and from the right, they are going to the same location. We will have an answer to this. If this was a jump, then the limit would be D and E, does not exist, because it'd be going to 2 separate places. But a hole, right, is kind of something, not that this is what the graph looks like, but just a hole is like, okay, well, it's just that the point isn't there, but the 2 sides are coming in. This is a 2-sided limit. They are going to the same place. Well, how are we going to figure out where it is? Simplify and try to plug in again. We're going to simplify this function. And you may have even noticed that from the beginning. Hey, doesn't this factor, and wouldn't one of those factors cancel out? Turns out, yes. Let's see, how would that factor, that numerator, x squared minus x minus 6? Well, one of the factors will be x minus 3. The other factor will be x plus 2. We can say, yeah, if we were to FOIL x times x, then we'd have plus 2x minus 3x, gives us the minus x in the middle, and negative 3 times positive 2. Okay, we see it. So these would cancel out. And we could trim it down to x plus 2. Once it's simplified to x plus 2, hey, I can plug in now. And my answer is 5. So at first, oh, it didn't quite work, but the 0 over 0 was like the giveaway. Hey, it's a whole. There is an answer. Simplify, and canceling that out, like canceled out what was producing the 0 over 0. But once that's gone, boom, we can get there. I'd like to kind of sit on this just a little bit more. I want to graph this thing, and we can even, kind of compare our answers with B and C and just kind of what happened. So let me share here. I'm going to hop over to Desmos. Desmo's been around a few years. Maybe you've heard of it in another math class. It's a free online graphing calculator. Really nifty, really slick. It's the opinion of myself and some others that the days of handheld graphing calculators are really coming to an end. So if you go to desmos.com and then you click on the graphing calculator, you'll get right into here. So I'm gonna just go ahead and type in our function, x squared minus x minus 6 over x minus 3. And kind of, oh, wow, now this is surprising, right? The graph turns out is a straight line. What's up with that? Well, it turns out it's the same graph as the simplified version, x plus 2. And that's exactly the same thing. There's one key difference though. At x equals 3, if we zoom in, that green function is going to have a hole where the purple one does not. So at 3 right there, let's see if I can kind of highlight and drag, and oh yeah, there we go. It's an infinitely small hole, so it doesn't show up right on the green graph. But if I kind of drag and go over, there's the hole at 3, where the purple graph will not have that hole. 3, if I can, there it is at 3, 5. That's filled in. So what happened? When we factored and simplified, when we canceled out those x minus 3s, we filled in that hole, which allowed us then to just plug in x equals 3 to get our answer. It did not change the limit, right? The limit here is still headed towards 5. We can see 5, right there. But algebraically, it canceled that out. It filled it in graphically, which then allowed us to algebraically plug in 3 and get our answer that we wanted the whole time. Okay, very cool. We got some other, switch it back to myself. We have some other examples, those other examples coming up, and we'll go further. I'm going to stop this video here. I'll see you in the next one.